Senior Research Engineer at Cloud Operations Department at IBM Research. He has over 8 years of research experience in the industrial labs. His research area and expertise lies in distributed systems and cloud. In the recent years, he has been active in the area of intelligence-driven cloud operations and enabling self-start properties, including closed-loop management, reliability assurance, and effective observability in cloud-native environments. He has also been a co-inventor of more than 20 US patents and co-authored multiple research papers at top-tier conferences. Additionally, he has actively mentored multiple students and collaborated with professors in various eminent academic institutions such as Boston University, IICs, IITs, IIITs, etc. He is also an ACM eminent speaker. He holds a bachelor's degree from BITS Pilani and MS from KTH Sweden. So we welcome you, Mudit. His talk is going to be a little more explosive. He is going to talk about something called as chaos engineering, and we let him define it. Thanks. Over to you.
Thank you, Rinku. Okay.
You would like to move or you'll start?
I'll move.
He is not moving, so this is fine.
No, I can move.
You want? Okay. Then let's use this. And this one, so you can.
Okay. So I have to keep both of them.
Yeah. So this one is for recording.
That's for actually for the speakers.
Okay.
This
You
one
attach
you
it to
can
your
just,
ID card and then that works.
oh, 1 second.
It,
You get to press it.
is there some feedback? If you would like this. No, sorry. It should work anywhere here. Sign it.
Good. Okay. All right. Good afternoon, everyone, and thanks, Rinku, for such a kind introduction. I have been part of IBM research for quite some time now, and like what Rinku said, my area of expertise has been in cloud and distributed systems. Couple of years back, for some of our project requirements, we delved into chaos engineering. So this talk is going to be about exploration of the same, and it is a new term that I want to introduce to you guys if you don't know already. How many of you know about chaos engineering already? None? Okay, great. How many of you know about pods, containers, Kubernetes? I'm sure all of you know by now, right? Microservices? Yes? Can anybody answer why do we need, why there is a shift from monolith applications to microservices now in the industry? Anybody? Just a brief answer around that. Why the industry is shifting towards microservice-based architectures as opposed to monoliths? Yes.
Because it allows the development of a single aspect of an entire system rather than forking the entire system and developing it. So it allows continuous integration and continuous development, which is the buzzword everybody uses.
Okay, very nice. You're very right. Instead of building a huge application as a single unit, you want to disintegrate into multiple functional units where each of those functional units can be developed independently, perhaps by a different set of teams, right? And then can also be deployed independently, right? And that's where an orchestrator platform like Kubernetes helps, that allows you to run these microservice-based applications in form of containers and pods. And of course, why do we need this is because you want scalability. If there is a monolith application, and if you have to scale that application, if there is more load to the application, you would have to create the exact same replica of the whole monolith, right? Whereas in case of microservices, you are only going to replicate the exact same function which requires extra resources. And this is a very common pattern, design pattern nowadays. Every company which are developing new applications, large scale systems, those are being driven using the microservice based architectures. Okay, any guesses what this is? Okay, microservices, yes, and what they are doing? Communicating with each other, right? So with this picture, what I want to emphasize is that in real world setups for large scale applications, um, let me just. So first one is are the microservices at Netflix, and second one are the microservices at Uber. And as you can already see that perhaps each of these systems consist of more than thousands of microservices, right? Now imagine the scale at which these systems are operating, right? Uh, all of these components in what goes on behind in the backend systems is all these little units interacting with each other to provide you a seamless end service, right? Whether it's Amazon or YouTube or Netflix. Now the problem with this is that while it's great for development, for CI/CD practices, for development, right, for scalability and performance, what is the apparent problem here? Right? Can anybody guess?
Services are like they can go down and they can respawn again.
Yes.
That is one problem. They are not stable. They always change.
So your services are always evolving, right? New services can get added, old one gets removed, some of them gets updated. So your interactions also change all the time. So overall, the complexity of the application, right, in terms of the interactions and the communication that's happening between them has also increased multiple folds with the rise of microservices, right? So that's a pitfall of having microservices based architecture. So in such circumstances, how do you ensure the reliability of such systems, right? It is not realistically or humanly possible to test such systems at this scale as you could perhaps do with monolith applications, right? So what exactly you want to do here? So as we said, application evolves all the time, right? And in such large scale systems, it's almost always given, no matter how good functional testing you do for each of your components, faults are inevitable, right? Faults are going to happen in your system. And especially for such large scale systems, it's not just one fault happening, it's multiple faults happening in different places all the time, right? So as a site reliability engineer or somebody who are in the task of ensuring the reliability of such systems, you have to ensure that there is no downtime for such systems, and you must be seeing that there are a lot of reports of large scale systems getting down, and even if they get down for an hour or for a few minutes,
Maybe we can.
okay, one more fault.
Yeah.
So use this.
Either
No, that will be too much.
for speaking or for recording.
Speaking, recording, we require that. Like the
Okay.
other option.
I think there is some.
I think like when they interact, there's some
Yeah.
start. Like, some information.
Yeah, you can put on here. So,
She comes around. Goes blue by. Hello. Oops.
It's okay now?
Yeah, sure.
Alright. So faults are inevitable in such large scale systems, bound to happen. So how do you still ensure the reliability of such systems, right? And where you cannot afford to have any downtime in such systems. So what do we do? Right. So there are a lot of reports around. You must have seen that Facebook went down, Instagram went down, WhatsApp is down, Twitter is down, and AWS is down, YouTube is down. And believe me, few seconds of downtime of such systems, and especially at a scales that they operate and the number of users that they serve, each second of downtime costs them millions of dollars. That's in terms of the cost, but also in terms of their reputation, right? So you do not want to have any downtime at any level, right? But as we talked about, faults are inevitable. They are going to happen. So how do you still ensure that reliability is the key question. Any guesses what should be done? Anything? Nothing? Should not do anything? Yeah, maybe.
Repeat your question.
So what do you see here, right? Let's burn it all down, right? Ourselves, right? Anyway things are going to fail, right? Let's do it ourselves. Um, and that's what that's where I would want to introduce you to chaos engineering, right? What is it about? Chaos engineering is about creating chaos intentionally. So you have a large scale system. Generally, people are very afraid of doing anything wrong with their systems. Oh, something would break, let me not touch it, right? Let me not do anything crazy about it. But chaos engineering is all about creating chaos in these systems. Do whatever you want. Your goal is to break the system, right? So whichever team is tasked with chaos engineering, right? Testing with chaos engineering, their sole purpose is to bring down the system, right? So there is this fight between, not real fight, but there is this struggle or tussle between the SREs and the developers. So developers would want to make their applications more reliable, and SREs, their task is to just break those applications, right? And why do we want to do this, right? Any guesses? Why do we want to intentionally create faults into the systems?
See any potential faults in future if it happen to occur in these applications.
Exactly. So you want to uncover any faults that are lying around in your system by yourself, rather than that happening when you are getting caught off guard, right? So you want to create such adverse situations by yourself to figure out if there are any weak points in your systems, and obviously if you find some, there would be corrective measures that can be taken, but all in a controlled environment. And this is helpful in making sure that your application is more reliable, right? As you would evolve, your application would become more reliable, right? And that's why you want to create this chaos by yourself intentionally. And this is a practice of chaos engineering, right? So it's a process of gauging your applications or systems resilience against adverse conditions. So whether it can withstand turbulent conditions or not. So like I said, chaos engineering is about intentionally injecting failures into your system. It started in 2011 by Netflix. That time there were no microservices, everything was running on VMs, and they created a tool called Chaos Monkey. Its only job was to, it was a very simple program, but it created a lot of let's say chaos inside Netflix, right? So what this program would do is would just randomly terminate any VM that is running, right? That's all. So they have a production system, thousands of VMs are running. It would go and just randomly kill any VM. So what it did was that it forced developers. So if your service is running on that VM, and if that VM is somehow chosen by that chaos monkey and it gets killed, your service is infected, right? So what it forced developers to develop more resilient applications, so that even one failure in one microservice is not going to impact them, right? So now with the cloud native architecture, and when I say cloud native, I mostly mean that microservices running in container orchestration platforms like Kubernetes, right? So there are a lot of so chaos engineering has become a topic of its own now, right? There are a lot of open source chaos engineering tools that are available, and not just killing any microservice, but there are n number of array of faults that you can inject into those systems. So it's a very widely accepted practice now. Most of the companies are practicing this in some form of the other, and there are a lot of open source tools are also available around this, right? So to name some of them: Red Hat Kraken, Litmus, Chaos Mesh, Chaos Toolkit, right? So there are many of them. In fact, uh, there is one chaos engineering tool called Cube Doom. So you can play the game Doom, and what it's going to do is randomly or whatever, right? In the form of the game, let's say you have your application running in some cluster. What it is going to do is while you play the game, your actual targets are different containers, right? So it's going to kill them in a fun way, right? Um, So, like I said, most of the chaos library supports wide array of different faults. You can kill a container, you can hog their memory, you can do the network corruption, you can add artificial latencies between the communications. At the application layer, HTTP layer, you can change the return code. Let's say something is supposed to return 200, in between you comes in and instead of returning 200, you start returning 404, right? So wide number of faults that are available are at your disposal to exercise, and this brings us to another problem. Right? This is just one example that how you can do the, for example, network corruption, right? So you can it requires different parameters. Where do you want to do the corruption? How much corruption do you want to do? Right? Whether it's 100% and for how long do you want to do? So if you think of one experiment as one test case, you will see that what test case do you want to run? Let's say network port corruption. Where do you want to run it? You have to specify which are my target ports or containers, and then you are going to say that how much corruption do you want to do? Right? I want to do 100% corruption or 50% corruption, and for how long do I want to do this? So all of this becomes a parameter for one single test case. And now you must have guessed, right? So the earlier picture which I showed you that contained more than thousands of services, and you also have different faults. Let's say you have more than 50, 60 faults, different types of faults that are supported by these chaos libraries. Each fault can take various inputs, right? How much, let's say how much memory hog do you want to do? Do you want to do it 10%, 20%, 30%, 40%? So how are you going to decide that what chaos I need to run? Right? So if you do the permutations and combinations, to be able to run chaos engineering or chaos test, this is a very this calculation is done on a very simple application consisting of only 12 microservices, and these are the number of test cases that you would have to run to be able to provide full coverage, right? So now you see the problem here. Anybody can tell us that what exactly, in which direction we are going here? See, while chaos engineering is great for you to exercise in creating these adverse conditions, how do you even know that what adverse conditions I need to create, right? If you just shoot in the dark, most likely than not, today's applications are very resilient, nothing is going to happen, right? So you have to, instead of shooting in the dark, you have to find right targets with right parameters so that the chances of bringing down the systems are higher, right? Of course, you cannot run all of these scenarios. It's not just possible in time-bound manner, right? So there is limited time to do that. You cannot do that. So you have to come up with a subset which is sufficient for you to be able to figuring out that as if you have run these all test cases. And that's where we are leading that this is a exact problem that chaos engineering faces today. Earlier it was fine with monolith applications or with VM based applications because the number of components were smaller, right? But as the number of components are increasing, as the number of faults that can be injected are increasing, your fault space is becoming so huge that it's just not possible, right? And what often people relies on is the current practice is that it's mostly intuition based, right? Let me pick this fault, inject it, and let's see what happens, right? It's also based on the expertise for the person who is injecting those faults. So you have to have domain expert who would have inside out knowledge of the application so that he can use that expertise in creating those scenarios which are more useful, right? Or at worst, it's random, right? You just pick some random test cases, inject them. If nothing happens, you claim that your application is all great, it's all resilient, but then in production one day it fails, right? Because your chaos engineering did not target the right scenarios. So these are the gaps that exist in chaos engineering. Again, this reiterates the same thing. So these are some of the insights. Most of the chaos test cases are hand curated. You need domain expertise. Another important one here is the fault types, right? So I'll come to this later, but we did a study of around 60 major outages that happened in last 10 years, and what we figured out from that information is that around 70% of the failures have a root cause somewhere in the infrastructure. Right? And it's also intuitive to understand that in cloud, your applications are running on top, then you have your middleware and then your infrastructure. If there is something wrong at the infrastructure, it would have a wider impact, right? Whereas if something goes wrong at the application layer, it's only that component or that application which is going to get impacted, right? So major outages or major failures are more likely than not are caused by infrastructure related failures. So this we have to keep in account while dealing with chaos engineering. Second one is time. We discussed that the fault space is so huge that it's not just realistically possible to cover them all. Continuity, right? So you have, as your application gets developed using CI/CD practices, so you also have to shift left for your testing, for your chaos engineering. So it's not just the production system where you are going to run your chaos engineering, but also in pre-prod, in test environment. This is just to widen the scope, right? If something is caught in test, great. Something is caught in pre-prod or staging or production, right? So this is just to widen your scope. And another one, important one is the realism, right? So I let's say I have 10 faults and I have 3 services. As we discussed originally about microservices, each microservice has its own function. So this is my question for you, that is every microservice that is running is going to behave in the same manner? No, right? Some of them could be heavy on network, some of them could be heavy on compute, some of them could be heavy on memory. So each microservice that is running in your system or each pod that is running in your system has its own characteristics, has its own personality, right? So you have to figure out that for this particular microservice, which are the faults which make sense, which are realistic, right? If there is a microservice which doesn't use network at all, okay, maybe that's a wrong one, but let's say uses very little network or very little memory, right? So would it make sense for me to go and inject 10 memory related faults into that service and not do any CPU related faults, which perhaps it is doing very heavy compute on that microservice? No, right? So we have to figure out, we have to take into consideration these characteristics of these microservices when figuring out that what fault should be injected into those microservices. So that's about realism, right? So we have to be realistic rather than, I have this gun, let me just randomly shoot with this gun. Maybe that guy is wearing whatever, right? Bullet chest or something. It's not going to impact. And last one is around complexity, right? So most of the chaos engineering libraries today only support an isolated fault injection. So here is one fault, you pick it, you inject it in some component, right? But what we have seen generally is any failure of significance that have capabilities of bringing down the systems, those are not caused by isolated faults. Generally, it's a cascade of different faults that occur, right? One thing would happen somewhere, because of that something is going to go wrong somewhere. So it's a chain of events that ultimately bring down the large scale system. So it's not always about one single fault, but multiple faults occurring simultaneously, either in sequence or in some complex combination. So your chaos engineering libraries should also support in orchestrating these complex real life fault behaviors. Right? So this is another gap which exists in chaos engineering. All right. So I would very briefly go over what we are doing in this space, right? So as we know that the original fault space is huge, and we want to come up with some realistic scenarios where the numbers are not so high for us to run all the test cases, and something that can be done in a time-bound manner while still providing you sufficiently good coverage, right? So what are the different things that we can do here, right? One is about historical incident and outage analysis. So what you can do is for that application or for that kind of application, you can see historical behavior. You can know that what are the different kind of faults this application has seen in the past, right? So those should be your first target for chaos engineering, right? Because those faults have occurred in the past. So there is a better likelihood that similar faults might occur. Or a similar class of applications, if certain faults are more susceptible, those should be your first candidate, right? And this way you can prioritize and discard some of the faults, reducing the fault space. Second one is application behavior analysis, right? Which I just talked about. So what you can do is you can run a workload against the application. It would be as realistic as possible. So when you run a traffic against the application which mimics a real-time behavior, your microservices are going to get simulated, are going to exhibit certain characteristics, right? On the other hand, you observe them using the telemetry or the observability tools and see that what is the CPU utilization for that microservice, or what is the network utilization or memory utilization for that microservice. And based on that information, you can characterize your microservices as CPU intensive, network intensive, or memory intensive. And accordingly, you only inject those relevant faults into those microservices. Right? That's another way for you to actually reduce the fault space. Another one is CTD optimization. It's combinatorial test design. Remember, we talked about that each single test can take multiple inputs, right? So if you have to do memory hog, should I do it 100%? Should I do it 50%? Or maybe just 10% would be enough? How would you figure this out, right? So this helps you in figuring out what should be the right value for parameterized utilization for those faults. And lastly, AI-based optimization, right? So how many of you have heard about reinforcement learning? Okay, many of you. So reinforcement learning allows you to search this huge, vast fault space and navigate them based on the exploration and exploitation, right? Where the faults which are capable to cause any downtime or any service degradation are rewarded, and the ones which are not, they are penalized. And based on this algorithm, you sort of navigate into the maze in figuring out that which are the scenarios which would be capable of causing the failure. And this is another technique to reduce the failure. So all of these different techniques, you don't have to use all of them, but given that first two are happening in the offline phase where you are not even injecting fault, before injecting any fault, you can analyze your application, you can do historical analysis in figuring out that how your application is going to behave to the injected faults. You can reduce the fault space, and then the online injection using the CPD optimization and AI optimization, you can actually significantly bring down the overall fault space. Yeah, same thing. Historical data analysis, right? So based on what faults have occurred in the past, you can prioritize some faults over the other. And in application behavior analysis, you analyze the application characteristics in figuring out that which faults are going to be more relevant for your application. For historical data analysis, again, this refers to the study that we have done, and here you can see that what kind of faults were often seen in large scale systems, right? So a lot of infrastructure related faults, network load, network latency, memory spike, right? Insufficient resources. So this gives us a clue that these are the faults which we should target more. Just going a bit deeper on application behavior analysis, here is one example of a small benchmarking application called Robot Shop. It consists of 12 microservices. So what we did is we put these applications against a workload and tried to see its resource usage in terms of the network, memory, and CPU. So here, if you see compute, right, there is a clear distinction between how much CPU each of these microservices are using, right? Using some algorithm, I'm not going to name the algorithm, there could be various ways of doing this. You can figure out that which are the CPU sensitive microservices and which are not, right? Similarly, for memory, you can figure out which are memory sensitive microservices, which are not, and which are network sensitive microservices, which are not. And once you have that, you can categorize them in network sensitive, CPU sensitive, or CPU intensive, and then try to match with the corresponding test cases. This shows you some of the results. So this is a matrix that you see here. On the y-axis you have different faults that can be injected, whereas on n-axis that you have different services that are running, right? And using this approach, as you can see, I would focus more on the right hand side picture. So the ones that you see here is our recommendation that these faults should be injected into those microservices, and where there is a 0, right, our recommendation is we don't inject those faults. So as you can see here is that you can, instead of, let's say, doing 200 tests, now you should be okay by doing just 50 tests, and that's the optimization. The last one is chaos using AI with reinforcement learning, which we already talked, that you can have a chaos agent that can penalize or reward different test cases based on whether they were able to cause any failure into the system or not. Right. So there is a more extensive work around this, which we are not going to go into the details today. My goal for this talk was to introduce you guys to chaos engineering. It's a fascinating topic to work upon, and it's most of the companies are now have a solution in some form or the other around chaos engineering, because as we discussed earlier, faults are inevitable. They are going to happen, so it's better that you catch them first before they actually occur in the production system. Whatever we discussed, a more advanced version of this, our work is open sourced with Red Hat's chaos engineering tool called Kraken, right? So here is a link for that. So you can go to this tool and try this out yourself and see that whatever applications. So I'm sure in your lab here on the previous days you must have learned that how to run applications on Kubernetes, right? So you can try running not just this, but you can take any chaos engineering library and run it against your application and see that how your application behaves, whether something breaks or not, and that way you can figure out that whether your application is resilient or not. With that, I will stop. Thank you so much.